plot spectrum. Not enough. Well, I can treat. Let's get some more sounds. Generate tone 3000 duration. Okay, let's give it 30 seconds. How? That should be enough. Analyze plot spectrum. Issa. I forgot what I created. What did we make? Generate tone 3000 plot spectrum. Okay. Not enough. Plot spectrum. There you are. Okay, the 3000 here. Okay, we have this peak here on the 3000 hertz. There you go, 3000. Okay, it's captured there. Yes. That's the grids we have there. Okay, so 3000 with an 8000 sample rate, that's captured well. Okay, let's make a different, let's make a different one, also at 8000. Sorry, didn't mean to do that. And I'm going to generate a tone of 4500 hertz, okay, for 30 seconds. Okay, and I'm going to analyze this plot spectrum. Mela, 4500. The sample rate is 8000 hertz. Nyquist frequency is 4000 hertz. 4500 is greater than 4000 hertz. Over here, our maximum measurement, okay, is up to 4000. It only shows us up to the Nyquist frequency. But you can see here that there's a peak reported on the 3500 hertz. And I generated a 4500. It's not shown here, but we have a peak on the 35. Why? Because of aliasing. Okay, the 4500, which is 500 hertz greater than the Nyquist frequency of 4000, is mirrored, and it's captured as 3500 or whereabouts. Okay, the way this spectrum works is that it doesn't have a value for each frequency. Okay, it will be approximate. So that 4500 is perceived to be at 3500 hertz. If I generate a tone of 6000 hertz, okay, close that, share this, analyze plot spectrum. It is perceived by the spectrum as a 2000 hertz signal, because 6000 is 2000 hertz bigger than 4000, the Nyquist frequency. It's mirrored into the range of perceivable sounds, and it is sensed as a 2 kilohertz sound. Okay, so the aliasing happens even when you are analyzing a sound. Okay, what this means. Okay, what this means is that whether you play a 2000 hertz sound or you play a 6000 hertz sound, if you sample them at 8000 hertz, they will show up the same. Okay, you will think that they are the same signal, because the intervening samples are not being captured. Let me explain that also with paint. So if I have...
Sir,
Yes.
mathematically, is it a subtraction of the wanted frequency and the sample rate? Because that's how it coincides.
It's a mirror, check. It's a subtraction, and then the difference is subtracted from the mirror. So 6 minus 4 is 2000. The 4, you subtract 2000 and you get the earliest rate. If I had 4500 minus the 4000, that's 500. It's 500 less than the Nyquist frequency. So
Okay.
350.
I thought it was being subtracted from the 8,000. So because if you get 4.5 and 8,000 minus 4.5 would be 3.5, which is what was shown. Same with the 6K. It came at 2K.
I think it works the same because, to be fair, if you capture, say, a 9000 hertz, okay, that's also earliest as 1000 hertz, not 5000. So 5000 is still beyond the 4, so it results in the same calculation. To be fair, it's in the same calculation.
Okay, I guess the paint will help here.
I try. I hope. So that is the lower frequency symbol. Okay. So let's see if I know what this out. So that and stay there. There you go. I always get the second clip wrong. And yeah, something like that. So what's happening is this. The samples being measured so this one is the proper actual frequency, okay, and this one here I should have colored it differently. I think I can now. Home there. Nah, but this one I can. Yes, this one I have to do that. So the black wave, okay, is the actual frequency. This colored, don't ask me what color it is, okay, is the earliest frequency. So because I am not capturing the actual frequency fast enough, all right, the system will think that I'm capturing this kind of frequency. All right, yeah, probably to also capture this one here. Okay, so 1, 2, 3, because it missed capturing this part here. Okay, when trying to interpolate to approximate the sound, it will think that it is this lower frequency signal rather than this higher frequency signal, because it doesn't have enough data to to guess, to interpolate the actual result. Let me just answer Glenn. Okay, let's see how to make it. Okay. So where were we? Yes. Okay.
There, but sorry if we've already gone through this. But won't this distort the sound with which is being recorded?
Definitely. So we're not saying that this is fine, okay? We're just explaining the phenomenon.
All right.
Just explaining how this is happening. And I can maybe extend this a bit more. Let's see. Okay, so if I capture this here with yellow. All right, so the common points between the the original frequency and the earliest frequency is where the samples are being taken. So when you take those 4 samples, you can't tell if it is the actual frequency or the alias frequency. So the system is like, yeah, I don't know what it was, but it sounded like this. So yes, of course, distortion, a change of timbre. That's why people sound different on telephone. Okay, now of course as we grow, as we use voice over IP, okay, it gets better. But on traditional telephones, okay, the voice of the person would sound a bit strange because certain frequencies, higher frequencies, would be aliased into a lower one. Of course, it doesn't apply for low voices, okay, mostly male voices. So the female voices are more prone to being aliased. And that's why I thought that my sick mother-in-law was my sick girlfriend back in the day. Um, anyway, so that's a next kind of an explanation of why frequencies bigger than the Nyquist frequency are aliased, are captured as a lower frequency signal. Okay, so let's write this one here, greater than Nyquist frequency. That's
Sir,
in black or gray. Yes.
out of curiosity, since we are saying that through this sound gets distorted, right? Is that the method used when when you hear, for example, a distorted guitar? When they use distortion in music, actually.
Issa, mela, distortion. First of all, it can mean many things, but most often distortion happens when the amplitude of the wave is greater than one. Is greater than one. So you lose the nice curve. Let me see. Give you an example. So if I have this
When it goes beyond the limit, biex niftehmu, where you have
azat,
one
azat,
minute.
azat. So let me make another one. Generate tone, something simpler for all say. Yes, so we have this. So if I amplify this one, infatti it won't allow me. It's gray because it's too loud. Somewhere. Yeah, like this is okay. But if I allow clipping, okay, I'm saying I'm fine with distortion, basically. So if I do this, see, it goes beyond. It goes beyond the range. Illy, the speaker will not be able to play that.
Okay.
So distortion happens in the performance of the sound because between here and here, the speaker will not move. It will just be stuck to the wind, to the glass, tipo. Issa, the distortion we have here is not an increase in volume, but a decrease in frequency. So it doesn't affect the actual loudness physically. It affects the timbre, okay, the harmonics and the timbre of the sound being listened to. So it changes the timbre rather,
Okay.
not the quality of the sound itself. Issa, I said it doesn't change the volume. It does, because as we've seen, lower frequencies are less audible than higher frequencies. So when it's earliest down, it is always the volume is also lessened down in its amplification.
All right. Thank you, sir.
As a result of perception, not physically. Okay, as a result of perception. You're welcome. Mela, we left off at a tangent somewhere, so let me recover that a bit. I will put this in the chat. I should have written aliasing here, aliasing explanation. So this summarizes what you need to know. Right? An assembling rate is used to capture a frequency that is higher than the Nyquist frequency. The partial data that is captured gives the impression of a lower frequency. an alias. This alias frequency is the mirror about the Nyquist frequency. Thus, 7 kHz is aliased as 1 kHz when sampled at 8 kHz. It reminds me of an ex-colleague who worked at reception, and whenever the principal passed by with his car, because he's coming back, coming for a lesson or leaving for a lesson, went off to parking, etc., he always finds him smoking a cigarette outside. And of course he's complaining, you're always outside smoking. But depends on when you pass. If you pass when on my break, obviously you're going to find me smoking, but in between, and you don't know what I'm doing in between. I'm actually working. That is the problem of not having enough samples taken every so often. So that is regarding sampling. Okay, that is regarding sampling. Of course, the more often the better, because you can capture more frequencies, you can capture more detailed analysis, but of course it also means that you need more space to store this data. More space to store this data. Did I mention the rates here? No. Okay, so what I'm going to mention now is not examinable, but I want you to know this part as well, which is the bit rate. Okay, the bit rate. What is the bit rate? It's what causes this pixelation here, this kind of blocky part. So we're taking a sample every so many milliseconds. Okay, what am I storing in that sample? How much data am I using to store that sample? So we could have 8 bits, we could have 16 bits, we could have 32 bit. Each time I'm using up so much data to store the sample. Now, the more bits I use, the more fine-grained is going to be my value stored. In what sense? So if I have, let's keep it simple. If I have a 4-bit sample, okay, for example at 8000 Hertz, okay, that would mean that in total I need 32,000 bits per second. Okay, that's the BPS, 10,000 bits per second. It's the size of the sample times how many of them I need per second. Now, when I have a 4-bit sample, theory. Well, if you remember your computer architecture, 4 bits will give us 16 possible values. 16 possible values. But the values, to be fair, are still in the range -1 to 1, okay, because we're storing a wave from -1 to 1. So those 16 basically mean that my precision, my accuracy, is you have from -1 to 1, that's a total of 2, all right, and division by 16. We are dividing that range of 2 over 16 possible measurements. So the detail there is of 1/8 of the amplitude. If I use 8 bits, I'm going to have not 16 values, it's 2 to the power of 8, right? If I'm not mistaken, that's 65535, 65536. So basically from -1, -1 to 1, that's going to be divided. That's leading us to have 2 division by 65536. So that gives us a 0.0040 zeros and a 3. 0.4 zeros and a 3. Whereas this one was 0.125. Okay? So the more bits you have, the more precise it's going to be. It's going to be to the nearest 0.0003 amplitude. Whereas with 4 bits, it's to the nearest 0.125. That's why it is blocky, because all values are approximated to the nearest value afforded by that bit rate. All right. You can imagine with 16-bit how much more you can have with 32-bit. All right. So the more bits you have, the more accurate, and also the less distortion you're going to have. If distortion is difference between the actual value and the recorded value, this this storage of a sample using bits, that's called quantization. Okay, that's called quantization. So you could say that sampling is discretization along time, whereas quantization leads to discretization, so making it discrete, not continuous, discretization along amplitude. So of course the y-axis here and the x-axis here. Okay, so brief explanation of quantization. Again, not examinable ma knowing that not that one deja għandhom dak. I copied this, I have nothing. Okay. But for example, there's variable bitrate. Variable bitrate means the number of bits being used is not fixed, but will depend according to the quality of the sound. Sorry, not the quality, the content of the sound. So it will vary according to the needs of the sound at that particular time. So it can vary accordingly. Okay, so sampling a long time, quantization is the approximation of the measured value. Together they determine the storage requirements of sound, and eventually also the same things apply when you have video, right? That is also part there. Okay, now something a bit different is the filtering process. I know we mentioned this last 2 weeks ago when we talked about speakers. Okay, the tweeter, we use the high pass filter, the woofer, we use the low pass filter, and the mid range we use the band pass. A bit more explanation here. So a low pass filter is, what is a filter? A filter is like a mask. Okay, a filter has an amplification value for a frequency range. Okay, for a frequency range. So in a low pass filter, frequencies below this cutoff frequency, so these frequencies down here, their amplitude remains constant. Okay, they are kept the same. But frequencies higher than the cutoff frequency, their amplitude is diminished or dampened. Yes, it is not an immediate cut. Okay, it goes down slowly depending on the sampling rate used for the filter. Okay, the higher the sampling rate, so the more samples we have, the faster we can cut off that frequency. However, because you're going to multiply this low pass filter with the sound in real time, it doesn't serve to have a very long filter. Okay, so you have to find a compromise between real time needs and how distinctive is the elimination of high frequencies. The high pass filter is a mirror image. Okay, so frequencies higher than the cutoff frequency remain at the same amplitude. Frequencies lower than the cutoff frequencies are dampened. If you realize the slope starts actually before the cutoff frequency. Yes, because up to -3 decibels, which is the measurement of amplitude, of loudness, which depends on amplitude, we don't sense the difference. Okay, so we can start diminishing the amplitude without our listeners actually realizing that we are dampening it. Now, a low pass filter and a high pass filter. With those two, okay, we can create a band pass filter and a band reject filter. How? Mela, if you consider this slope and this slope, okay, they are basically this slope and this slope. Okay, they are the slope of the cutoff frequency and the slope, of the low pass filter and the slope of the high pass filter. So to have a band pass filter, what we need is that the cutoff frequency of the low pass filter is higher than the cutoff frequency of the high pass filter. Okay? So if this cutoff frequency is lower than the cutoff frequency of the low pass filter, we will only allow those frequencies between those two cutoffs to pass through. And that gives us our band pass filter. Let me show that quickly here again. I can draw it. So if I have my low pass filter, okay, with a cutoff frequency, and then I have my other, which is the high pass frequency, okay, with a cutoff frequency higher than that of the low pass filter. Basically, only those frequencies between these two are allowed to pass. The others will be blocked either by the high pass filter or by the low pass filter. Okay, only those in the intersection are allowed to pass. So I can build a band pass filter by using a combination of a low pass and a high pass, where the cutoff frequency of the high pass is lower than that of the low pass. The band reject, so the one which will keep the low frequencies and the high frequencies but will eliminate a central band of frequencies, can also be made out of a low pass and a high pass. And at this time, the cutoff frequency of the low pass is smaller than that of the high pass. Okay, the cutoff of the low pass is here. Okay, smaller than the cutoff of the high pass, which is over here. So these are allowed to pass, these are allowed to pass, these in the middle are blocked by both filters. So they are not allowed to pass. So it is possible to create these two out of these two basic filters that we have here. Explained over these few slides as well. Where do we use them? Okay, apart from the speakers. We mentioned aliasing. All right. So in order to eliminate aliasing, we can use a low pass filter before sampling. In what sense? Mela, if I have the example we had before, okay, an 8000 Hertz sample rate, and we have a 6000 Hertz sound, what will happen? It will be aliased as a 2000 Hertz signal. Okay. Remember, Nyquist rate is 4000. But if I use a low pass filter at 4000 Hertz, the 6000 Hertz sound will be blocked, okay, and therefore not aliased as a 2000 Hertz signal. So these filters can help us clean the sound in order to avoid these wrongly perceived sounds. So this one here is use of a low pass filter to avoid aliasing. In fact, okay, as I said, our ears act as low-pass filters with a cutoff frequency of 20 kHz. Our eardrum is too lazy to dance, to jiggle to the frequencies higher than 20k. It can be used to control high-pitched sounds like S's in microphones, or reduce high frequencies for the woofer speakers that we saw last lesson. So yes, the high-pitched sounds like S in microphones, that's when they do the mic check, and you're and the sound engineer is controlling the low-pass filter to make sure that the S works well. Of course, you can see these also in some seasoned singers. Okay. For example, comes to mind right now when Jay-Z was with Linkin Park, and as they were waiting for the sound engineers to set them up, he was talking a bit with the crowd, and he was saying like, "See what I'm saying?" Right? He was using the S in his statement so that the sound engineer could control the quality of the S. High pass. So the high pass removes low frequency sounds, and this is most used with tweeters to avoid them having to also play the low frequencies, but just focus on the high frequencies. In the case of the Hooger vest, of course, I want a low pass frequency, a low pass filter. Sorry, a low pass filter at 200 Hz. And also an amplification, so to amplify those frequencies as they are sensed. The bandpass filter, as we said, combination of higher and lower. It's used for the mid-range speakers and also to extract specific sounds from a noisy clip, okay, or to extract lyrics from a song, for example. Not perfect, but you can remove the high frequency instruments, the low frequency drums, etc., and just focus on the lyrics. Useful, for example, when you have journalists reporting live and you want to remove the wind from the microphone, for example. Enough if they are in a feast and you have the flares and the fireworks, and you want to also remove the low boom of the fireworks and the high-pitched sounds of the flares. Again, a bandpass filter there would be great. A band stop reject can be used to eliminate a specific sound from a particular audio. For example, you are recording a lecture or a presentation, and someone's alarm goes off. Okay, teet, 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 teet. That's a high-pitched sound which you can cleanly remove. But if you have someone who sneezes or a door bangs shut, that's going to cover all frequencies. So it will be quite difficult to actually remove it using a band stop filter. You will end up removing all the sounds just to remove that. Okay. Chipmunk sound. Okay, chipmunk sound. And I don't know, Darth Vader sound? I don't know, possibly. What happens when sounds sampled at a specific rate are played back at a different rate? In my days, this would happen when you record with flat batteries. Right? When you record sound with a flat battery, the mechanism doesn't have enough power to move the tape fast enough, and then when you come to play the sound and you use fresh batteries, you get chipmunk sound. It gets too fast. That's a problem, okay? Because you have recorded it badly. You need to have flat batteries to play it to the correct one. On the other hand, you would realize you have flat batteries when you're playing music and it all play slowly, right? So that's power. That's power stuff. Here we're doing specific rate stuff. I think I can maybe show something here. So what happened? This okay. So this one is at 44 hertz. No, too much. This one up here. This one up here is 8,000. Let's make a new one. Sorry. So track, add new mono track, and let's do that at 8,000. Okay, and I'm going to generate a tone of 1,500. Okay, and let's give that just 10 seconds. Still too much, but anyway. Okay. Yes. What happened? Well, probably you can hear it. Let me just turn this speaker on here. Okay. It's a bit too much. Sorry. I'll generate something a bit more audible. Yeah, tone of 440. Okay. And that sounds like. Okay, I hope that was audible. Issa, if I change the rate, okay, I'm gonna change it to 16,000 hertz. Whoops, what happened there? Let me undo that. Okay, the duration here is of 10 seconds. It's 10 seconds. I'm gonna change the rate to double the 8,000 to 16. Whoop, it's 5 seconds now. It's 5 seconds. What does it sound like? Different. Okay, so before it was okay, so changing the playback rate, okay, has changed the duration of the sound and has changed the pitch of the sound. Let's see why. So I have an audio clip in this example here of a 1,500 hertz sine wave. That's 1 second, 1,500 cycles in 1 second. And these were sampled at 4,000 hertz. So in each second, I took 4,000 samples. So my sound clip has 4,000 values. And originally, those values were spread over 1 second. But if now I play it back at 8,000 hertz, jiġifieri, I need 8,000 samples to have 1 full second. That's what 8,000 hertz playback rate means. But I don't have 8,000 hertz. I don't have 8,000 samples. I have 4,000 samples. And 4,000 samples will only fill half a second. So there you go. The playback is now for half a second, not for 1 second. And because the original 1500 hertz, okay, that was captured, occupied a full second, okay, those 1500 cycles occupied a full second, because now they occupy half a second, because those 4,000 samples can only fill in half that 8,000 hertz. So if 1,500 cycles that previously fit in 1 second are now fitting in half a second, to have a full second, I need 3,000. Okay? So that piece of sound now is being heard as if it was a 3,000 hertz signal. So doubling the playback speed doubles the frequency, halves the duration. Let's do it again. Doubling the playback speed from 4,000 to 8,000 doubles the frequency from 15,000 to 3,000, but halves the duration. Instead of 1 second, it's half a second. And it's all based on how many samples I have. Okay? Originally, I captured 4,000 samples. I'm playing them back at 8,000 samples per second. I only have 4,000. I can only fill half a second, so that's the shortened duration. And that original 1,500 cycles that occupied a full second are now squashed to fill half a second. Because I have squashed them, because the wavelength is now half the length, wavelength is the reciprocal of frequency. So shortening the wavelength increases the frequency. Halving the wavelength doubles the frequency. So we get to hear it at 3,000 Hertz. That's how we get the chipmunk voice. Okay? That's how we get the chipmunk voice. We change the playback rate for your signal. The opposite is of course true. If I have an audio clip of 1500 Hertz, sampled at 4000, but played back at 2000 Hertz. Okay? So I only need 2000 samples for a full second. I have 4000, so I fill up 2 seconds. So it's twice as long now. It's not 1 second, it's 2 seconds. But now, those 1500 Hertz, which were occupying 1 second, they now occupy 2 seconds. So in 1 second, I have only half of them, 750 Hertz. So that sound will be played and you will perceive a lower pitch sound for a longer duration. That's why if you play with flat batteries, it's lower and slower. All right? I remember I had a fun time doing, it was my son's birthday. I think he was 2 or 3 years old. And he had this teddy bear. And yeah, he used to watch Barney at the time, right? So while he was asleep, I managed to record a bit of a video with Barney, with the rhinoceros and the Styracosaurus, I think PJ, I think was his name, PJ, and this bear, right? And with my voice, I made the voice of PJ, which is a bit high pitched. I made the voice of Barney, and I made the voice of the teddy bear. And then when he woke up, I showed him the video clip, and then I took a video of him watching the video clip. It was fun to do, but for once. I still have it somewhere. Okay, compression. So compression is about, first of all, compression of size. Okay, compressing the amount of space needed to store the sound. There's lossy compression and there's lossless. Loss means, am I able to recreate the exact original sound data? Data, be careful. Am I able to recreate the original sound data? Lossy compression, no, you can't get back the original data, but it is still perceived the same. It is still perceived the same. So the difference here is between content and reception. Okay? With lossy compression, the content is different, but the perception is the same. With lossless compression, the reception is the same because the content remains the same. All right? But lossless compression is not able to get the same compression ratio as lossy compression. So MP3, okay, is an example of a lossy compression. You can get up to 90% compression, but it can still sound like the original system because they make use of redundant data, which is removed. But when you play it back, it's still there because you only remove the redundant data. Redundant as in there's more than one copy. Okay, you left only one copy and you removed the rest. For example, if I have a stereo system and the sound source is right ahead of me, then my left and my right channels are the same. Do I need both of them? No. I can store one of them and use that to, at runtime, to regenerate the other channel off of it. Okay, so that is the recording part. Took me 1.5 hours, jeez. Okay. The audio mixing now. How do we process the audio that we are dealing with? We have like 8 elements here that I will go through. You can get more detailed information about this from the link I have at the bottom. That's my citation, if you like. And what we're referring to here are keywords or jargon related to mixing. Yes, we get compression again, but this is going to be a different form of compression. All right. So, so audio mixing is when we are combining audio together. Okay, we have a scene with multiple sound sources, and we want to create the full sound experience. The first one, of course, is levels and panning. So levels is how loud these sound sources are. And of course, the loudness depends on how far am I from them. And also panning. Panning, as Gavin pointed to before, are the speakers able to indicate where the object is by having the speakers closer to the virtual object's position sound louder than the other speaker. Okay, so panning is again based on loudness. And of course, yes.
Wouldn't if you have like stereo speakers, that would be soundstage though? Or am I confused?
Come again.
Wouldn't if you have a stereo speaker system, that would be soundstage instead, like when you have like 2 speakers, but like you can differentiate where the drums are coming from or where the guitar is coming from.
Yes, that's what we're referring to. But in that case, you have a fixed sound source. All right. What I'm saying here is, for example, if the singer, okay, if he's moving from left to right on the stage, then there should be a panning of the sound as well on the speakers as well.
Okay. All right. Okay.
So that what we listen to matches what we're seeing.
This is literally panning from left to right. All right.
Exactly.
All right. Thanks, sir.
Thank you for the question. The other one is subtractive equalization and editing, where, as I explained earlier, with a high-pass filter, for example, you remove unwanted sounds, you remove the wind, you remove some hiss that you have, the S's of the speakers, or eliminating or muting unwanted performances. Okay, so subtractive equalization is modifying the harmonic aspect of sound, okay, the frequency aspect of sound, whereas editing is about timing, all right, eliminating or muting unwanted performances. The prank that you put on people when we had the sound recorder with the switch on and off. You tell someone to say, "Hey, Dli, tell me Jien minix bahnan," and they say Jien minix bahnan. And of course, you turn off the recording on the minix, so when you play it back, it says Jien bahnan. See, I recorded you saying that you are stupid. I am not stupid. You turn it off with the not, and it becomes I am stupid. Prank of a teenager back in the 90s. Issa, compression. Okay, what is compression here? Mela, a problem that our ears have is sensing low amplitude sounds after listening to high amplitude sounds. Okay? Think about going to the disco. Okay, and you will fucking swim. It's been ages since I went to Pachelbel. You go to a disco, okay, it's go disco, and loud music, and your ears are bombarded for like an hour or two, and then when you come out, right, you can't hear crap, right? Your friends are talking to you like, what? Because your ears are like drunk with sound. So That also happens in the immediate. Okay, if you have a soft sound also at the same time or just before or just after you have this higher amplitude sound. This is called the dynamic range. Okay, the range between the softest sound and the loudest sound. You want to have a shorter dynamic range by minimizing the difference. Give me a couple of seconds, coming back. Okay, so we do this by limiting the loudness of the louder parts and boosting the loudness of the quieter parts. So setting specific limits on how much of a frequency is let through, so the loudness of the frequency, and boosting the quieter portions. So you increase the soft parts and you lower the loud parts, diminishing this dynamic range. Like this, you provide a more consistent and balanced overall sound. You might appreciate this more when you compare, for example, you're watching a television series, okay, and adverts come in. And that's when your neighbors or partners or parents, whatever, but Shaylo, it's too loud, all right? It wasn't loud, the adverts are loud. Because, of course, the series would have been balanced, would have been used compression so that the overall sound, you don't need to go increase the volume, lower the volume, increase the volume. Okay, it's a constant volume. And the adverts wouldn't know what kind of compression the actual series is using, and they would have their own range of amplitude. So when there's a switch to the adverts, there's this change in loudness. Of course, if you have advanced televisions, they can try to keep the overall volume constant as well. Effects processing. So we are here in the post-processing, adding some effects to the sound. Adding reverb, so reverberations, that is the echoes of a wall. Delays and modulation. Modulation, we took a look at some of them. We had amplitude modulation, we had frequency modulation. Okay, we're adding effects on these sounds. Before we had subtractive equalization. Okay, we removed frequencies from a recorded sound. With additive equalization, we are increasing levels at particular frequencies. We are modifying the sound to sound louder, okay? Modifying the timbre of a person. And in this case, this is all synthesis. Okay? With subtractive, we were working with real data. Here, we are inventing new data. Okay? It's synthetic. So it's less faithful, less realistic. Sometimes we want to control instruments as a group. So grouping instruments will help us control the overall sound of a section of the music. So for example, the drums and percussion would be in a group. The melodic instruments would be in a different group. The backing vocals and their effects would be in a group. The lead vocals would be in their own group. So then you have not the master volume of everyone, okay, but the master volume for every group. And you can control all of the members of the group using this specific sound slider. What if we can automate this? Okay, adjusting dynamics of each performance based on contemporary audio events. For example, a radio DJ, okay, could have an automatic volume diminishing when they are speaking. All right, so they could start the song, but when they speak, sometimes on purpose so you don't record it. All right. When they speak, the volume lowers down so that they can be heard. Yesterday, I was watching the European Parliament. Okay, because of course there was the meeting about the unfortunate war going on, and you had different translators for different people, and it was a bit laughable when the translator could be barely heard, and I was more listening to the original speaker than to the translator. Sort of, come on, man, speak up. Do your, you're doing your work, but you can't hear it, because of course there was a problem of levels. You needed to lower the level of the original speaker, and raise that of the translator. To be fair, that process was done, but they were speaking so low, amplitude-wise, that it wasn't enough. Okay, they needed more. They needed more upping of their level, amplification of their level. And then finally, you print the final mix. Now, this in the old days actually meant that, it was written to tape. You finally have your your final version on tape. Nowadays, that doesn't count. I mean, it's an export to MP3. Now there's more thing to fix, so let's fix it better. Export again. Back then you couldn't. Okay, back then once you're printing the final mix, it was too expensive to do it again. So you had to be perfect with the output, and basically have your print. Because you would have multiple tracks, okay, being printed on a single tape. So each instrument would have its own recorded track, but then you want to combine all of them onto a single track that is going out to your customers. So you needed to record all these tracks onto one tape. And that requires time and effort and the process. So it's not something that let's do it again. No, there's not enough money to do that process again. Okay. The final part that we have here is about studio organization. Where to put what, and how does that work? So I got these from a page about a commercial digital audio workstation, which had an app. Okay, which had an app. So it was trying to give an idea of how you could work with your own setup to do this. Nowadays, for example, if you go to, I won't tell you the name, but there's a computer shop in Eclean, right? They have an exhibition, the streamer desk, right? So you have the desk, you have the microphone, you have the camera, you have the USB steamer deck with buttons, so you can choose what configuration you want to have, a nice white television, and of course the kick-ass PC. What they had missing was the light. So when you're streaming and you're on the side, being shown there. So in that case, it's the mic which was relevant to us here. But you also have to consider the acoustics of the room, and also what is close to you. So on the left hand, you do have 2 rows in this. Okay, it's not necessarily 2 people, but at least there are 2 roles. There is the performance, okay, whether it's a musician performing or you're playing a game. So there's the performance, and then there's the engineer who is recording this. All right. So if you've seen the Foley example, okay, of the fisherman cutting the fish, we had the two sound actors, okay, the 2 performers, and behind them we had the engineer recording all this. Now, if you are alone, you have to do these on your own. So the bottom left solo recording setup is where you have your desk with the digital audio workstation. What's a digital audio workstation? It's like Audacity. Okay, that's what they were called wave editors back in the day. A more pushy name now is digital audio workstation, and of course they have a bit more features. So you have your desk there. You have your mixers and lines on the studio rack. You have the MIDI controllers to your 5 o'clock. All right. Now with MIDI controllers, what we mean there is basically keyboards. I think I can make Jamie present. I've seen him and he didn't make it, and all the rest are here, so I can save. So MIDI controllers are quite small, to be honest. So they don't need the size to generate the sound physically, right? But what they need to do is to transmit the information. So they are small keyboards, like this one, with a cable out that basically feeds into your mixer. All right, and yeah, apart from musical notes here, you also have pads that can select specific options and configurations, and you also control the sound from up here. There are some few examples here, as you can see. Even pads, right? A pad controller which outputs MIDI, but so it's not using traditional music, but rather enough. Linkin Park uses it. Ten, 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 ten. That's something that you would have on this one. Yeah, and of course you get multiple sizes and also combined pads and keyboards. That's over there. Microphones here so that you can sing, right? For the lead singer, you are the only ones who are singing as well, but you might also record your backing vocals with that as well. And then the guitars here as well, guitars connected to amplifier, and that amplifier may be connected to the studio rack as well. So yeah, you would need to have the stuff all around you so you can turn around and use the stuff as necessary. How am I able to play everything at once? No, you don't. You record them separately and then you layer them in your digital audio workstation. All right. For example, I don't know if I still have this. Audacity project G. You know you've seen in yeah, I think it's this one. You've seen quite a lot of pandemic time recordings of choirs, right, playing together. Okay, and my choir also decided to do this, and at first they were like trying to record real time on Zoom. Forget it, because the timing doesn't work. And then what we had to do was to have individual singers singing their piece. Okay, and I said, listen, unless someone starts doing it, it's not going to happen. So I began. I think I started with this one. Sorry, you're going to listen to my voice for now, singing. Wait a minute, this one. So just one. Now, that is the tenor voice, and I am not a tenor, right? So I was making a bit of an effort there. Then you had something which was the bass, which is something similar. Wait, what happened here? No, I don't want to draw, I want to play. Sorry, there. So a lower pitch. which sounds so crappy when you play it alone, right? And then you have the alto, so the female low pitch. That's my wife, not me, of course. Soprano, similar. Up there. Then I got my daughter to play the flute. And here we had the backing track. Which was someone else singing. And I also had the guitar for it. So that then you have to use recording them all separately, and then you have them all playing. So you just do solo, no, mute, off, turn off, 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 and off, and you get a cacophony that sounds like this. And basically then this got sent round, and you had all the other members doing the same recordings to it, then combined all together, and you got something presentable. But yes, that's what the printing, the final mix is about, and that's what your recording is going to be. You're recording each one separately. Okay, you do need to have a backing track sort of to give the tempo. And then you're going to combine them all into one using the digital audio workstation. The middle one is when you have two people, where station one would probably be the engineer, okay, where he has the studio rack controlling all the settings, the software, and give him something to do, playing it with the MIDI controller, while you are playing with your own MIDI controllers, on microphones, maybe the guitars, but he's controlling everything. Now, when you have an app on your tablet, right, which can connect to your PC software, then you can emulate this kind of dual setup, but you have your door remote available to you. Okay, so you can control the desk from far away, sort of, using the tablet as your controller. This is sort of kind of an idea of how to have this hybrid recording setup within a small studio that could be your room. But of course, we also want to see what a proper studio would look like. And here I managed to find two different configurations. Where again we have a separation between the engineer and the performers. Starting with this colorful one here on the left. The upper half is the control room, okay, where you have the engineer with speakers, so he can listen to the output of what's happening in here, and a waiting room for, I don't know, whoever's here. There's a window, actually a sliding door here, and with window panes, so that the engineer can see through and communicate with the vocal booth, where you're going to have the singer, and he can also look through here to communicate with the main room, where, for example, you're going to have the drums or the backing vocals, the choir, whatever. And another room here for the guitar and amplifier. You also have some measurements here, and you can come in and go out from here as well. Now notice that the vocal booth is separated from the main room, and the guitar is separated from the main room. This would be a soundproofed room. Alright, so from over here you can't hear the vocal room, and likewise. and from here to here, um, he of course the engineer can of course hear you through the microphone. They might have also a controllable speaker system to communicate from here to here. I was once a backing vocalist for a song competing for Song for Europe back in my late teens, and we had gone to the studio of Philip Vella. I imagine if you're Maltese, you know who Philip Vella is. He has quite a few songs competing there. And I remember that one of our members wanted to ask me something, so she asked the question to Philip so that Philip could speak it to me through the microphone. But before he had the chance to tell me that, I gave him the answer already. And he sort of looked at me like, "Can you listen?" I'm like, "No, I can lip read." So I could see through the window. I could lip read her question, and I answered that. So they have to be separated so that they don't contaminate each other's sound. Okay, if I want, in fact, in my example, for the guitar, for example, here, you could hear the backing track. Oh, sorry. You could hear the backing track, and that backing track was playing to my headphones, right? So the headphones are not really so great because the microphone can capture the sounds through the headphones. You don't want that, okay? You don't want that when you're recording the individual instruments. The other layout, this other layout here is a bit different because the control room is in the middle, which means that the engineer can have full view to everyone, okay, to the office, to the lobby, to whoever's going to the live room, the guitar booth here, the closet, for hiding something. But again, it's important to have visual communication, but those rooms have to be soundproofed. Soundproofed and possibly even without echo, okay, what we call anechoic chambers. They basically have egg egg containers, okay, or heavy curtains, okay, which either deflect the sound so it doesn't bounce off, or absorb it. Okay, or absorb it. Even in cinemas, when you touch the wall, it's not a hard wall, but there's a curtain in front of the wall in order to absorb the sounds and not let the acoustics of the room affect the sounds of the film that's being played to you. Yeah, so some considerations there about the setup, about the properties of the rooms. And of course, you also need to be soundproofed from your neighbors. Okay, so that the neighbors don't hear you, they want to sleep, and you don't want to hear them screaming at each other either. So that is also an important part. If you manage to get a room outside in the middle of a field, that's great. But here in Malta we don't have that luxury, or at least not everyone does. So, yeah, that one there is something also to keep it in consideration, and something also to look out for. Okay, if you happen to have the opportunity to visit one or to on a radio station, for example, okay, have a look and be sensitive, be observant as to what's happening. Something else that you might want to do is to observe an orchestra. Okay, observe the different instruments that partake in this. Why? Well, one, I wouldn't say watching an orchestra on television, right? That's not half as fun, but actually and not even at a theater or at a pantomime, because usually they are in the pit where you can't see them. But when there's an orchestra playing very close to people, like in a feast, when feasts start becoming a thing again, right? For example, here in Zabar, we have the orchestra playing in the side nave, so people can be just next to them watching. Hearing this collaboration of instruments together really makes you experience sound in a different way. Great. As usual, I managed to finish bang on time on the last slide. So what we've done today is we've covered the last half of this set of slides, the basic studio skills. That's the last topic you have for the exam. And we looked at recording, mixing, and mastering. With recording, we looked at sampling and the notion of Nyquist rate and Nyquist frequency. That is the relationship between sampling rate and frequencies, the maximum frequency we want to capture. You want to have a sampling rate which is at least twice as much as the highest frequency. We then looked at filters, low pass filter, high pass filter, how we can combine them to get band stop filter or band pass filter, and how we can use them to avoid, for example, the notion of aliasing. Okay, aliasing, which happens when you capture sounds which are higher than your Nyquist frequency. They sound as a lesser frequency. And then we covered a few the notion of compression. Yes, that's for space compression. We looked at what happens when sounds are played with a different rate, which could be, a creative use for that. I don't have maybe the proper sound for a banshee shriek, okay, but I can shriek and then I can change the playback rate of it and make it sound so much more scary. You might recall the song Dance Monkey, right? And Dance Monkey it's a lady singing, and she has an effect on her voice. And we wanted some music, but we had Godzilla in mind, right? Not a monkey. So what we did was we changed the playback and then modified the sound so that it goes back to its original length, and we got a low frequency version of Dance Monkey. And you could attribute that. You could imagine that's Godzilla, not Godzilla. Sorry, King Kong. I said Godzilla twice. Sorry, compare it to King Kong. King Kong playing, singing the Dance Monkey, but a much lower frequency. I don't think I have it here, do I? Family, can I label? No. Okay. Right, so compression. Then we looked at some aspects of audio mixing, and yes, so one lesson that you should take from this is, if you can get the sound right naturally, okay, that's going to sound much better than if you had to fix it later. Okay. So if while recording something, someone sneezes, okay, first of all, get them out of the room because they might have corona. No, re-record the whole thing, re-record the thing. If not the whole thing, you can edit it out if it's possible. But if something bad happens, and I'll remove it later, and if you're actually able to do a retake, you better do a retake, because it will. To remove that sneeze, you will remove other stuff which is important for you and will diminish the quality of the sound. Okay? The later you handle a problem, the bigger the problem becomes. Okay? The solution is less effective the later you take it. Okay? Don't forget compression there is not about space compression, it's about the dynamic range compression. the difference between the softest sound and the lightest sound. It's kind of like doing a histogram equalization of an image. What's that? In an image, if you do histogram equalization, you brighten the dark spots and you darken the bright spots. So you have an even distribution of light everywhere. Similarly, but for sound. We've explained these. And then we took a bit of an idea of studio organization, the two roles you have within a recording studio, and how if you have a separate person, that's great. Then they have their own room, and then you have your own setup of the room. You still need visibility, okay? You still need visibility between the lead singer, the guitarist, and the drummer, okay? Because they need to coordinate between them. But sound-wise, you want to capture them separately in order so that you can then control, mix them with full control for you. Okay, that's the end of that section. So up till here is what you have for the exam. We do have another chapter that we will be handling, but that's more to do with the assignment. Okay, and that's what's how many slides? 22 slides, so that's another couple of lectures there, which can happen after the exams. I'm not saying they should. I'm just thinking of how many lessons we have left. As far as I know, your exams are soon. Don't scare us. Yes, I'm just checking. Someone knows the actual dates. استنى ميت شحات
30 طيبين
30. Okay.
Kelpo għaladna, sorry.
Mela, here I have 24th. And we are second, so we have at least one more lecture. That's on the 16th. Because 30th, there are exams going on. So you have the 16th there. I'll be able to start covering that topic. It's there's I can cover that in one. Don't worry. Yeah, can finish that. So there would not be the need for lessons after the exams, but I will do tutorials for the assignment because I will need to make sure that you got the software working, and that any issues you could have with the project, I can actually help you with that.
Sir,
Yes.
I don't know obviously if the rest of the class agrees on this or not, but given that next week is our last lecture pre-exams,
Not next week, 16th.
Sorry. The next lecture is the last lecture before the exam.
Okay.
And the topic that we are going to cover is not.
It's not for the exam. Yes.
I don't know if the others agree, but in my opinion, it would make more sense that the next lecture
revision
would be a revision, and then that lecture be done after the exams.
I'm happy with that.
I need the input of the others on this.
I agree. Kenneth. I agree.
Yes, there's agreement.
Thank you.
Yes, of course. So we'll do not a quick run through, but a relatively quick run through of the topics that are for the exam. I can tell you that the exam paper has been submitted already, so I am that's covered. But again,
hopefully is not as enticing. Not enticing. Sorry, that's not the word. As difficult. Let's put it like that. As was the first assignment.
It's
in
not.
In terms of reading only.
The exam is not in terms of reading. No, No, the reading part of the assignment compared to the exam. Now, I think you will find the exam quite. I mean, you have an hour for the exam.
Yeah.
Just
Yeah,
one.
yes, and I think you need less than that. Actually, let me just let's mind. No, the 1 hour when it was combined. It's not combined now. I'm saying you definitely have much more time than you need to answer the exam because there are multiple choice questions in it.
Okay.
Okay.
So
Good.
you have less time needing to write. It's not all multiple choice. So there are parts where you have to answer them, but there's quite a good bunch of them which are multiple choice. So when I do multiple choice questions, they might be
Tricky.
quite tricky. Yeah. So don't dismiss them. Don't dismiss them. But again, it's an exam which is 30%. I mean, the major effort is on the assignment, and that's why it's challenging. Okay, especially the first one. The second one should be less challenging and more fun to do. But as I said, the first one it's a must pain in order to enjoy the second one, or enjoy doing the second one. How do you enjoy doing an assignment? You will tell me after you've done it. Okay, after you've done the assignment, you will tell if you enjoyed doing that or not.
It all depends on the assignment. Then we'll wait. We'll wait for the publishing of the
Echo,
assignment.
echo, 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 echo. Okay.
Okay.
So by next time we meet, I hope that everyone will have given me their first one, their first assignment, because that's the so by the previous Sunday would have been the maximum. The idea is to start giving me stuff to work on, right? And I already have a bunch to work on already, and then I'll have a second batch straggling coming in so that I can keep up with that.
Just out of curiosity, sir, for the first
Yes.
assignment, when do we have an estimated time as to when we would be receiving the results for that? Approximately more than.
Yes, so what I hope to do is to have the feedback for everyone by the time you finish your last exam.
Okay.
So once you finish the exam, you can then next phase of this for the assignment.
All right. Okay. Thank you very much.
If I finish them before, I will publish them before. But sort of my target is so that when you finish off from that ordeal, you come charged for this one.
No problem. Okay, sir. Thank you very much.
Okay, you're welcome.
Thanks a lot, sir.
Thanks.
You're welcome.
Thanks.
Thank you, sir.
Have a good
Thank you.
evening.
Good evening.
Thank you.
Likewise.
Good evening.